My dear student, today let us see some examples, important examples of Lebesgue integration. First, we will be giving an example where the strict inequality occurs, in Fatau's lemma. Strict inequality. Fatau's lemma is very important one. For any sequence of function, we have this, Fatau's lemma statement. Let me write it down first. For any sequence of non-negative measurable function, what the Fatau's lemma says that integration of the limit infinity infimum fn dx, it is less than or equal to limit infimum integration fn dx. This is Fatau's lemma. What is this? Fn is a sequence of non-negative. It is a sequence of non-negative measurable function. This is true. So this is a less than equality. So most of the time it is equal, but we want to give an example where the strict inequality happens, means this side is strictly less than this side. So we want to give an example of that theorem. Okay, so let us see one by one. So let us consider this sequence of function. Let f twice n minus 1, that means when n is odd. Okay, this is, you have a sequence of function f1 f2 f3 f4 f5 up to infinity. So this is the case when odd. In case of odd in the sequence, the function is defined by this characteristic function 0 1. In case of even, it is defined by this one. All right, so what is this? Yeah, let me tell you. So now you are considering this sequence of function, say f1 f2 f3 f4, and it is going. So this is odd. So this is equal to how much? This is characteristic function 0 1. Okay, so this f1 is equal to characteristic function 0 1. So this is even. So this is equal to how much? This is equal to, this is even, therefore it is characteristic function 1 2. This is open interval, like this. So this is odd, therefore it is also equal to characteristic function 0 1. This is even, this is, therefore it is equal to characteristic function 1 2, like this. So this is the sequence of function. Characteristic function, they are non-negative measurable function because the intervals are measurable. So their Lebesgue integration is defined, that we have already done that one. So this is the sequence of function. Now for the case 1, let us see when x, when x is outside the 0 to this interval, then what do you have? Let us see, starting from n, then fn x fn plus 1 x is equal to like this. Okay, so that means if the point x is outside 0 2, then it is not in 0 1 also, it is not in 1 2 also. Therefore according to the characteristic function definition, the value, so for every x outside 0 2, this is also 0, this is also 0, all are 0. Okay, so means this set consists of a singleton set 0. Okay, so if you check infimum, in this case, what is infimum of the singleton set 0 is 0. So infimum k greater than or equal to n, fk is equal to 0 in this. Therefore it follows that if you take supremum of the such, so when k is equal to 1 you have 0, when k is equal to 2 you have 0. Okay, like this 0 0 0 function. For that, if you take supremum, it is again 0. All right, So supremum infimum k greater than or equal to n, fk is equal to 0 in this situation. That means what? When x is outside the domain 0 2, okay, the limit infimum function is equal to 0, right? So let us see when the case when x is a member of 0 2. In this situation, let us see if x is a member of 0 1, then if if n is odd, then it is equal to 1, right? So then the next is even. In case of even, x should be in 1 2. So if x is in 0 1, that is 0. All right, so that means what? This sequence of function is equal to 1 0 1 0 like this when n is odd. When n is even, this is equal to 0 1 0 1 like this. So ultimately these two sets are equal, they are exactly equal to 0 1, this finite set. So if you take infimum of this 0 and 1, so obviously it is 0. So infimum, you know infimum k greater than equal to n, fk is equal to 0. So case number 3, let us see when x is a member of 1 2 of an interval, what happened? Yeah. See, so f n x, f n plus 1 x, this sequence of function starting from n is equal to, when n is odd. Okay, since x is a member of 1 2 closed interval, when n is odd, this function is equal to characteristic function 0 1. All right, so therefore since x belongs to 1 2, this is equal to 0, and next it will be 1 like this. So 0 1 0 0, 0 1 0 1, it is like that when n is odd. So similarly when n is even, so this sequence of function is, it is 1 0 1 0 like this. Okay, right? So therefore what? infimum k greater than or equal to n, fk is equal to 0 in this case also. Okay, so that means what? In all possible cases infimum k greater than or equal to n, fk is equal to 0. So if you take supremum of this one, right, so supremum of this one, you will get supremum of all 0 0 zeros. So what is the supremum of this? It consists of only 0, therefore its supremum is 0. And from this, the limit infimum function is equal to how much? Limit infimum function is equal to 0. The function which is denoted by this one, we call it limit infimum function. It is equal to 0, and integration of a 0 function is 0, so we have this one. Okay, so in the case when limit infimum is inside the integration, limit infimum fn dx is equal to 0. This is what we get for this sequence of function. So next let us see, integration fn dx is equal to, it can be written in this form: integration from minus infinity to 0, then from 0 to 1 in this domain, then from 1 to 2, then from 2 to infinity like this. Okay, this integration can be written like this. All right, so in case if x is a member of minus infinity 0, so it is not in 0 2, therefore the characteristic function value is 0, so this part will be 0. All right, similarly beyond 2, the characteristic function is also 0, therefore this is also 0. So only thing remains these two term, this term and this term. So this is equal to 0 1 closed interval integration fn dx plus 1 to open interval integration fn dx. So this you get. So that means what? If x is a member of 0 1, then this part is equal to 1, integration of this part is equal to 1. But because this is a characteristic function, if x is a member of 1 2, then it is, this part is 1. So when it is 1, this will be 0. When it is 1, this will be 0. That you understand according to the definition of the characteristic function. So only possible value of this one is equal to 1. So integration fn dx is equal to 1. Integration fn dx is equal to 1. So what you have, integration fn dx is equal to 1. This is true for all n greater than equal to 1. Alright, so f1 dx is equal to 1, f2 dx is also equal to 1, f3 dx is also equal to 1, like this. So that means if you take infimum of this 1 1 1 starting from n, k starting from n, k starting from n, so you get all 1 1. So infimum of this set is exactly equal to 1. Alright, then you take supremum. You take supremum infimum k greater than equal to n. You take this one. It is also 1. You are taking supremum of 1 1 1 like this. So it is also equal to 1. Alright. So what is the function? Then it follows that limit infimum integration fn dx is equal to 1. Okay. So then you see, compare equation 1 and 2. Equation 1 says it is 0. Equation 2 says it is 1. So there is strict inequality is there. That means integration limit infimum fn dx is strictly less than, integration limit infimum integration fn dx. So this is an example which support the strict inequality of the Fatau's lemma. This is a very important example. Okay, so similarly you can look for similar examples. All right, so this is very important. Next, let us see another very important example. You already knew that integration of this function 1 upon x is equal to infinity. That in your class 11 12 standard integration you know it. Graduation level integration also you know it. Okay, but now we are going to prove it using the Lebesgue integration. Okay, using the definition of Lebesgue integration. All right, so that we are going to start it from the definition of Lebesgue integration. So what Lebesgue says that every continuous function is measurable. Okay, so you know that 1 upon x or x inverse is a continuous function. In this domain 1 to infinity, it is a continuous function. Therefore it is a measurable function. Okay, 1 upon x is a continuous function, therefore it is a measurable function. Also it is non-negative. It is obvious in this domain 1 to infinity it is non-negative. So it is an example. It is a function which is measurable as well as which is non-negative. So according to the definition of Lebesgue integration for non-negative measurable function, so this is a function which is non-negative measurable function. So its integration, its Lebesgue integration is defined. So let us see what is the value of this Lebesgue integration. So also we have proved that if this 1 infinity is a bigger domain than 1 to n, for any positive integer n, 1 up to infinity, this is a bigger domain than 1 up to n. Alright, so same function, bigger domain, that means what? This will be strictly greater than this one. This we have done it. This we have proved it using Lebesgue integration definition. So then that means what? So 1 up to infinity means, so notation you can write integration from 1 to infinity 1 upon x dx. This is it is less than, strictly less than integration 1 to n 1 upon x dx. This is true for any n. When n is equal to 100 also this is greater than this side. When n is equal to 1 billion also this is greater than this side. So for any n, as n tends to infinity also this is greater than this side. Okay, so that is the concept. And now let us see what is this. So you know that this integration can be break up into some of the disjoint domain. So 1 to 2, 2 to 3, like this, up to this side. Actually this is finite case, so let us break up into this integration on the domain 1 to 2. Okay, 1 included, 2 not included. All right, like this integration. So this is equal to how much then? So in short notation, this sum you can write like this: k going from 2 to n integration from k minus 1 to k 1 upon x dx. Right. So then 1 upon x is strictly greater than 1 by k in this domain. All right. So for any value in this domain, 1 upon x will be strictly greater than 1 by k. Okay, reciprocal function is decreasing, so k is the greatest one, therefore 1 by k will be smallest. Okay, will be smaller than any other value between k minus 1 and k. Right. So 1 upon x is strictly greater than 1 by k, so in this domain. So therefore if you this one, if 1 upon x is replaced by 1 by k, then this is strictly greater than this one. Okay, so then what, this integration is this is simple function, characteristic function. So this is equal to how much? This is equal to 1 by k. Okay, so 1 by k. So what is this sum? K going from 1 to 2 to k going from 2 to say n, k going from 2 to n. So therefore when k is equal to 2, how do you get? Integration 1 by 2, 1 to 2, so that is equal to 1 by 2. So 1 by 2 plus 1 by 3 up to 1 by when k is equal to 2 up to 1 by n. So you have some like this. Let me tell you, you have some like this: 1 by 2 plus 1 by 3 plus 1 by 4, and then plus 1 by say n. Let us see. So this sum will be strictly greater than 1 by k, where k is any member 2, 3, 4 like this. Okay, this total sum is strictly greater than 1 by k, where k is equal to 2, 3, 4 any member. Okay, so in that way what you have, that is why I am writing this one. Okay, so the k going from 2 to n, 1 by k, so it is this one is strictly less than this one. All right. So but this sum as n tends to infinity, goes to infinity. Right, this is divergent series. So this sum tends to infinity as n tends to infinity. Okay, so the right hand side is infinity and the left hand side is greater than the right hand side, but this is going to be infinity as n tends to infinity, though ultimately this is going to be infinity. All right, so integration 1 to infinity 1 upon x dx is equal to infinity. This is how you prove, just using Lebesgue's definition of integration. We have proved that integration 1 to infinity dx by x is equal to infinity. Okay, so we are not using the all concept or all definition of integration of class 12 standard or graduation level, but using Lebesgue integration definition, we have proved that integration 1 up to infinity dx by x is equal to infinity. Okay, so there are lots of examples, similar example, so you can do. Next time I will give you some more example. Okay, so for today let us stop here.